Hello students, this is the Unit 5 Lesson 1 video on altitudes. We're going to be talking in this unit about different lines that you can draw inside triangles and their particular properties. We're going to use those properties to try to answer algebraic questions and also to graph on a coordinate grid. An altitude is a specific kind of line that you can draw inside of a triangle. Here's a little preview of what they look like. And as a matter of fact, in any triangle, you can draw 3 different altitudes. Most of the time, they're going to be drawn inside the triangle. Sometimes they'll be outside, but we'll give you all that information coming up. Let's take a look at the learning target. According to the target, you can apply properties of altitudes to solve for unknowns. Remember, this is the key phrase that means we're going to be using them in an algebraic scenario. And then write the equation of the altitude of a triangle. In other words, we're going to be writing the equation of a line. And you know that that is y equals mx plus b. So using similar stuff that we've done in the past. For the do now, it asks us for each problem to draw in the line segment that's described. For this question, it says that a tent is set up for a camping trip, and the camper places a tent pole into the tent to keep the tent from collapsing. I'll leave it to you to figure out where that is. And then two observers see a plane flying overhead, and they want to determine how high that plane is above the ground. All right, pause the video, try this one out, and then see if you got it right. All right, here's that first example. If you're trying to place the tent pole into the tent to keep it from collapsing, it would go directly here in the middle. And I want you to notice that this line that we drew that represents the pole, this line is perpendicular to the ground, right? You would have to put it so that it's straight up and down so that it wouldn't tip over to any side. So we call that perpendicular to the ground. It forms a right angle. And similarly, we know that the height of the plane above the ground, that's going to be measured from where it is directly downwards to the ground. That line that we just drew, that dotted line, is perpendicular to the ground. And we didn't know exactly where the ground was, so we had to extend this horizontal line so that this vertical line touched it. One thing that you should notice about both of these situations, both of these scenarios, is that we drew so-called perpendicular lines that were at right angles to each other. And we also were able to draw them so that they intersected a vertex, one point on the triangle. So in this triangle, the top point here, we called that the vertex. We drew a line directly from the vertex down to where the base was so that it was perpendicular. From here, we started at the vertex, and we couldn't draw a line that intersected the base that was perpendicular, so we had to make our own line and extend the base so that they would eventually be perpendicular to each other. That line and this line, and any line that goes from the vertex to the base and in a perpendicular fashion, is called an altitude. You might have recognized the word altitude from when we were talking about planes. Altitude of a plane is just how far it is above the ground. That's the vocabulary word that we use for the height of a plane or an object above the ground. In geometry, the altitude of a triangle is a very specific line that you can draw. And I'm going to fill in these blanks and then we'll talk about them. Okay, as you might have guessed, the first word is altitude. The altitude of a triangle intersects one vertex of the triangle, vertex meaning point. And it is perpendicular to the opposite side. In other words, it forms a right angle with the opposite side. And it turns out that since there are 3 vertices, the plural of vertex is vertices, 3 vertices in every triangle has 3 possible altitudes that can be drawn. And last but not least, the altitude can be drawn in either the interior or exterior of the triangle. This altitude is drawn in the interior of the triangle. So is this one. They're inside the triangle. Whereas this altitude, just like the plane example, is drawn on the exterior of the triangle. So that's one key piece of information that you need. An altitude can either be inside or outside. That's not true of all the lines we're going to be learning about this unit, but altitudes can be either inside or outside. In this exercise, we're supposed to look at all of these triangles and draw the altitudes as dotted lines. And we're supposed to notice any patterns. So take a moment to try to draw these out on your paper and then draw 3 altitudes for each triangle. Okay, here are a couple of main patterns that you should have seen. Let's take a look first at the green lines. Notice that both of these triangles are so-called obtuse triangles. We call them obtuse because there's one angle in them that is larger than 90 degrees but less than 180 degrees. And in both of these obtuse triangles, you can see that the altitudes intersect outside the triangle all in one central point. Right? The way that we drew these altitudes, incidentally, is we went from every single vertex to the opposite side. Every single vertex to, well, we couldn't go to the opposite side, so we had to go downwards until we got to an extension of the opposite side. Notice that we extended these lines. The reason we had to do that is because if you tried to draw a line, an altitude, through this triangle like this, and tried to make it so that it was perpendicular to the base, well, it just couldn't happen. So we had to swivel it out here so that it was perpendicular to the base. So all of these, or both of these obtuse triangles have altitudes that are drawn, and two of them are outside of the triangle, and they intersect outside the triangle. One other thing that you should notice is that for the right triangle here, this right triangle has two altitudes that are the same as its sides, which should make sense because starting from this vertex down to the opposite side, there's already a 90-degree angle in the triangle. So this is an altitude and this is an altitude. The third altitude here is drawn from the vertex to the opposite side, but notice that they all intersect at a point, and that point is on the edge of the triangle. Here we have a scalene acute triangle, and all of these altitudes are drawn inside the triangle and they intersect inside the triangle. Moving on to these special triangles, this is an equilateral triangle. Notice that the three altitudes intersect directly in the center of that equilateral triangle. And then last but not least, in this isosceles triangle, you can see that the altitudes also intersect all at the same point, and they're inside the triangle. So one thing that you should observe is that all three of the altitudes are always going to intersect at one specific point. This point could either be outside the triangle, on the edge of the triangle, or inside the triangle. And again, all of the altitudes follow the rules for altitudes, which means they are passing through a vertex and they're perpendicular to the opposite side. All right, moving on to problems. In this first model problem, the equilateral triangle ALT has an altitude from point M through vertex A, from point M through vertex A. This is called an altitude, so we're able to say that it has a right angle. It asks, what is the measure of MAT? Well, we know it's an equilateral triangle. So, in an equilateral triangle, all the angles are the same measures. So I've identified all the different angles that are 60 degrees. Since it's an equilateral triangle, all angles are 60 degrees. Now it's talking about the measure of angle MAT, angle MAT. And you can see that this angle is not the entire top angle, it's just part of the top angle. Knowing what I know about the rest of the angles, though, I can put this together using the triangle sum theorem. Since I know that this angle here is a 90-degree angle, and since I know this angle here is a 60-degree angle, all I need to do is figure out this angle here, which is angle MAT. So I put all those three angles into the formula, set them equal to 180, and I solve, and I get angle MAT is equal to 30. Of course, 30 degrees. Moving on to the next problem, the triangle shows XYZ, or the triangle shown is XYZ, I should say, with altitude PY drawn. If it tells me that the altitude is PY, that means it is at right angles to the opposite side, which is XC. If XC is equal to 6, which is labeled, PZ is equal to 2, which is also labeled, how kind of them, and XY is equal to 5, which is similarly labeled, what's the measure of the altitude? Well, we're looking for the measure of the altitude. Keep in mind that this is PY. And we're looking for measures of sides, so we're given some of the sides, but we're not giving everything. One thing that we can find out pretty easily, though, is the side PX. We know the entire side here, XZ, is 6. This part of it is only 2, so that means PX is equal to 4 centimeters. Now that I'm looking at this shape a little bit more closely, I can see that there's actually 3 different shapes here. This original XYZ triangle, and the 2 smaller triangles that make up that larger triangle. Specifically, this triangle is a triangle that I know 2 of the sides of, and I'm missing a 3rd. This triangle is a right triangle, and I know that because it is a triangle with a altitude as part of it. So since this is a right triangle, and since I know this side is 4 and this side is 5, I can use the Pythagorean Theorem to find this missing side. And as you may remember, the Pythagorean Theorem says a squared plus b squared equals c squared, where a and b are the legs of the triangle, and c is the so-called hypotenuse. So I know that the hypotenuse of this triangle is 5, and the 2 legs are 4 and py respectively, so I substitute those into the equation. Then I solve. I'm getting py squared is equal to 9, which means py is equal to 3. I found my measure of the altitude because py is the altitude. It should be 3, of course, centimeters. Good thing I remembered my measurements. The next problem that you're going to do in class is the check for understanding, but I want to skip over that because I have one more thing to show you today, and that is how to write the equation of an altitude. In order to write the equation of any line, y equals mx plus b, you need 2 pieces of information. You need the slope and you need the y-intercept. When you're trying to draw the altitude of a triangle, you know that the altitude of a triangle is perpendicular to its base. Perpendicular has to do with slopes. And it passes through the vertex, and that y-intercept is going to be based on one point that it passes through. So using this information, we're going to be able to write the equation of the altitude of a triangle. So look at the triangle here. Triangle ABC is drawn, and we want to draw an altitude through point C. So I could just draw any old random line that goes through point C, like there, for example, but I don't know whether it has right angles to the opposite side. So what we're going to do is we're going to try to figure out where that line is supposed to go. So first, we find the slope. Side AB from here to here is the opposite side of point C, so we can find the slope using the slope formula. M is equal to y2 minus y1 over x2 minus x1. So looking at this example, A is negative 2 comma 4 and B is 1 comma negative 5, so we're going to use these values in the slope just the slope formula, and we get a negative 3 as our answer, or negative 3 over 1, whichever is your pleasure. However, we know that the altitude is supposed to be perpendicular to this opposite side. So once we found this slope, now we need to find the perpendicular slope. In other words, the negative reciprocal slope to negative 3. And that means we got to take negative 3 and flip it upside down and make it its opposite sign. So our negative reciprocal slope is 1/3. Now I know that the slope of my altitude is going to be 1/3. Once I have the slope of my line, all I need is the y-intercept. So moving on to the y-intercept, we want the altitude from point C. We know it's supposed to go through this point. So we already have a point that we know is going to be on this altitude. So we can use that ordered pair in order to solve for B. So we'll take this x value and this y value and substitute them into y equals mx plus b along with the slope that we just found, the slope of the altitude, and then solve for b. That's the only unknown that we have in this equation, and we're looking for the y-intercept, so we're trying to solve for b. Solving this equation gives us 4/3, so 4/3 is equal to b. Now let's put those two parts together. Since we now have the y-intercept of the altitude and the slope of the altitude, we're able to put them together to make the equation y equals 1/3 coming from here, x plus 4/3 coming from here. Couldn't be simpler. I would go through this next problem with you, but of course it is the check for understanding, so you need to do it in class to prove that you know what you're talking about. Which means this is the end of the video. Today we talked about the Unit 5 Lesson 1 lesson on altitudes. Alright folks, good luck studying.